Right. Okay. So I will just do a brief introduction because I think most of the attendees already know Andy. Okay, so Dr. Andrew Bunger is currently a professor working at the Department of Civil and Environmental Engineering at University of Pittsburgh, and he's also our current ARMA president. So I'm very, very happy to have Andy to give this talk and wish to inspire the future potential speakers. So, Andy, it's your turn.
All right, thanks so much. Yeah, on to the future leaders and to, all that the future leaders do for ARMA. It's a little bit of a misnomer because the future leaders are not only the future but also present of ARMA. So thank you to all of you who are part of the future leaders. Um, and yeah, I hope that 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 all of us here who find ARMA to add value to our careers will stay engaged, and it's certainly a great experience being a part of leading ARMA and being a part of ARMA at that level. So today I want to talk about a couple of research issues I've come across in rock mechanics over the past few years. Um, they're both they're related by the fact that they're topics that arose when we tried to, capture what was going on in experiments with a classical hydraulic fracture model. We saw a shortcoming and came up um, with some modeling responses to try to practically capture what we observed in both the lab and the field. And so I want to go through these stories today. So the first has to do with time dependence in rock breakage. And before I get to hydraulic fracturing, I want to talk about just time dependence generally in the breakage of rocks. So you can see it in a number of different configurations. This is one that we spent a little bit of time looking at, just classical three-point bending. And it's an experiment probably many of us have been a part of. You have a set of supports, you ramp up the load P, and you ramp it up until the rock breaks. Um, and if you look at the guidelines for these types of tests, both in rock and concrete, kind of buried in there, there's this sense of loading rate and bounds on loading rate. And if you ask yourself why, it is because rocks are time dependent in how they break, even though we often don't think about that. And so one of the things we got interested in was how do rocks break in a delayed manner? So instead of just loading it until it breaks instantly, what if we find where that instant breaking load is, but don't go all the way there? We go to a load that's maybe 70 or 80% of the load that it would take to break the rock instantly, and then hold it. And during these series of experiments, we measured acoustic emissions during the lead up to failure. Here's an example of the cumulative events over time. This experiment ran for a bit over 20,000 seconds, so like 8 hours. And we can see acoustic emissions being generated through that entire period. They have a fairly, and this is under a constant load. So this is the load here. Um, and so this is sometimes called in the literature brittle creep. It's creep-like because of that. You get these different stages of development of the breakage. Brittle in the sense that it's producing acoustic emissions. And they have kind of an interesting character. So if you look at the location of the acoustic emissions, I'm just looking in the X direction. X is measured along the sample. The eventual observed fracture is here in the red dashed line. We see when we first load this burst of events, and then there's this kind of depletion. And then there's a turnaround where the rate begins to pick up again. You can see the rate increasing just, by your eye, by how dense these events are in time. And they coalesce around the eventual fracture surface. So this is, I think, evidence of what we typically call in breakage of quasi-brittle materials as microcrack coalescence. What we believe is happening here is we have kind of the most prone sites to break are breaking in a time-delayed manner here. We kind of deplete those sites, but eventually there gets to be such a density of microcracks that have grown that, one or two microcracks might beget a new one near them. And you start getting this one microcrack begets another, and that's where the coalescence kicks in, eventually accelerating into breakage. Now, if we look at the event rate, we can see that the event rate actually decreases for a bit under half of the life of the specimen. So for, in this case, a bit over 40% of those 8 hours that the specimen survived this load are declining event rate. But then it turns around and for hours is experiencing this slowly increasing event rate before a final burst at the end. So we found this kind of interesting because actually there was this long period of time where you can see it's accelerating to failure. And if we didn't want it to fail, you could imagine we could have intervened. Now, this actually occurs over a wide variety of time scales. So if we look here at time scales varying from tens of seconds, hundreds of seconds, getting up into the 10 to the fourth, 10 to the fifth seconds, this particular test ran for 100 and almost 200,000 seconds. So we're talking like 2.5 days. If you step back from it, the shape is basically the same. There's a period of decline for a bit under half of the life, and then this slow acceleration. The order of magnitude of cumulative events remains roughly the same. So the event rate is smaller for these long-term tests, and the cumulative is kind of remaining in the same order of magnitude. Okay, so clearly the failure of rock is intrinsically time dependent. I didn't show it, but these tests, roughly speaking, these tests that last longer are under smaller load, as you might imagine. Okay, so how does that impact hydraulic fracturing? We got interested in this problem from a practical perspective. We were funded by Schlumberger for this work originally, looking at this problem of what do you do when you're fracturing for stress testing from packers, where the packers have a limitation and sometimes they can't achieve breakdown. But there's this kind of field experience that says, well, if you hold for a little while, maybe you can eventually get initiation of a hydraulic fracture. So we wanted to study this phenomenon and see if it was something that could be used for anything with practical or scientific relevance. So what we did was this was it was kind of a typical lab scale hydraulic fracture. We created a packed off region, an isolated region where we pressurized. More typically, one would inject it like a constant rate, create a hydraulic fracture, study whatever it is that's of interest. But instead here, we ramped up to a pressure that was insufficient to create a hydraulic fracture right away, but held that constant pressure and measured the time to initiation. So how does it look? This is a case in granite. By the way, we did this in granite. We did this in limestone. We did this in sandstone. We did it in shale, though the shale tests were very messy because of the variability of the shale, but not because they weren't failing in a delayed manner, just hard to predict because every sample was so different from the last. So let's look firstly at water in granite. And you can see in these experiments, almost instant breakdown at 16 MPa. If one holds 12 MPa, so 75% of what's required for instantaneous failure, but you're willing to hold it for a few hours, you can eventually initiate hydraulic fracture initiation and growth. With glycerin, the instantaneous breakdown pressure is higher, the slope is different, but the overall behavior is the same. So viscosity dependent, qualitatively the same, where there's this uh, time dependence that persists over a wide range of time scales. Similar in sandstone, there's this persistence over a wide range of time scales. One of the things that's interesting in sandstone, this is a very permeable sandstone. So let me use that to transition to how we model this. Um, I mean, even in granite, these from the perspective of diffusion of fluid into the pore space, these long-term tests are completely drained conditions in granite. In sandstone, everything here is drained. So it creates a problem if you're trying to model this and as we were thinking initially in our heads, oh, this is a poromechanical issue that you have diffusion of the fluid, and so you're kind of inheriting this time to breakdown from the time scale of diffusion. The problem here, especially if you look at these sandstone tests, the time scale for diffusion into the near wellbore region is way smaller than these hundreds and thousands of seconds that we see to breakdown. And even in granite, these are completely drained tests. The nature of diffusion is that you get a non-time dependent undrained solution when you do everything fast, and you get a not time dependent drain solution. And the transient part that connects those is fairly narrow in terms of the time scales that it impacts. That's not what we see here. We see time dependence over a wide range of time scales, and that is not consistent with what we can model using diffusion. What we ended up having to do was actually change our propagation condition to recognize that the propagation condition embedded in our hydraulic fracture model, which said that K1 fracture, the stress intensity factor, would be compared to K1C, the fracture toughness. And if K1's less than K1C in the original model, nothing's happening. Fracture is not propagating. But what we believe is actually happening is that the fracture can propagate subcritically. We actually use a Charles law, classical way of considering subcritical crack growth. And we can make a modification of our tip condition in the hydraulic fracture model. So typically the hydraulic fracture model says that propagation happens when the width achieves a certain value, when there's enough, when the width compares and equals something that is related to K1C. What we find when we rearrange this thing is that we get a velocity dependence here. And that actually lets the crack propagate really slowly at subcritical values, and then it accelerates as K1 approaches K1C. So when we substitute this into our hydraulic fracture model, and we use a value of n that is kind of independently, but not fully independently determined. And what I mean by that is we independently determine the range for n using double torsion tests. That's a classical test in the lab. And we find for granite that double torsion tests tell us that n should be in the range of about 25 to 35. Now, what we find in practice is that our hydraulic fracture initiation model is way more sensitive than the double torsion tests to the specific value of n. And so we fit n within the range that we found from the lab. So n is found to be a bit lower in sandstone from double torsion. Within that range, we find that our experiments are fit very well. Now, practically speaking, beyond the initial question of initiation of hydraulic fractures for stress testing, I think it also plays into this practical problem of how do you initiate multiple hydraulic fractures in this scenario that plays out many times every day throughout the oil and gas industry, which is trying to initiate and grow multiple hydraulic fractures within a single pumping stage of a multi-stage horizontal well stimulation. And what do we mean by that? So let's make a little thought experiment. Let's think about two locations along a horizontal well that a hydraulic fracture could initiate. And I'm going to represent the fact that one of these is going to be easier for the fracture to initiate by a longer notch. So that's a cartoon representation that it might have lower strength, or it might have lower stress, but at some level, one location is going to be the easiest place for the fracture to initiate. And so when the pressure is ramped up, it reaches some point and that fracture starts growing, then what's going to happen next? And the model would say that the pressure falls off. Experience would say that there could be some continued increase in the bottom hole pressure beyond this initiation, but maybe only by a couple hundred psi. Reservoir variability is typically often more than that. And so the other option, the only other way that we can initiate this fracture is that it initiates at some subcritical pressure. So here's what we think is probably happening in probably most cases, is that the pressure goes up to some level. Often it's held at a constant value even as fractures start to grow using design of the perforations that keeps the pressure high. This is sometimes called limited entry, and it holds that pressure at a constant value. Now, this fracture and any others in the stage that haven't initiated yet have this problem that they're now only going to see pressures that they saw before and they didn't initiate. But if they're able to initiate and grow at subcritical pressures, then they can eventually start growing with some delay time. And so then the question becomes, is that delay time greater than or less than the pumping time? And can we do something in order to reduce it? Something with fluid chemistry, fluid rock interaction, fluid viscosity. What can we do to reduce those delay times? Because that could really be important to achieving a uniform stimulation that has fractures growing from all of the entry points. Okay, so that's the first topic that we discovered, is that the hydraulic fractures grow in a delayed manner, and they can initiate in a delayed manner, and there's probably some really practical cases where that's important. Now, jumping over to another hydraulic fracture modeling topic, and this has to do with field scale experiments, is evidence of width constriction. And I'm going to show this in the context of an application that may not be familiar to everyone, but this is subsurface pumped energy storage. And the premise is to create a storage lens by a process of hydraulic fracturing. So pumping viscous fluid into the subsurface. Here, this lens is shown in a horizontal orientation. And what is a lens? It's a hydraulic fracture that's no longer growing. So this lens is created in such a way maybe that there's some material that is packed into the tip so that the fracture tip doesn't see the pressure anymore and it stops growing. So that from that point, it can be inflated and allowed to deflate with its storage being a capacity for energy storage. So the idea is to inflate the lens by pumping water during high power production times. So you run surface pumps using solar cells, for example, and then to produce water from the lens during low production times to drive a turbine at the surface. And the pressure and flowing rate are in proportion to the difference between the rock density and the fluid viscosity. This is a technique. There's a couple of companies working on these, but this pure lens storage is the originally pioneered by QuidNet Energy, and is a topic of ongoing field demonstration. So where I got involved was in modeling this lens inflation and deflation. It's in a lot of ways similar to a classical hydraulic fracture model. It's similar in the sense that you have an elasticity equation that relates the width to the pressure. So this is pressure minus in situ stress, has plane strain, elastic modulus, crack radius. I've written this part here in black. with AIJ being a displacement discontinuity method based matrix that I set up. You can use whatever your favorite elasticity solver is. That was just convenient for me. And then we're going to see what this bridge stress is thing. We'll see what that is here in a few minutes. There's a continuity equation which says that each little section of the fracture has fluid that can flow in and flow out. This part here is the divergence of the flux Q. So that says the difference between what flows in and what flows out is accommodated by a change in width or fluid loss to the formation. So kind of classical, there in this model, there's a classical leak off and a pressure dependent leak off. I won't go into details about the leak off today. There's a fluid flux equation that relates fluid flux Q to the gradient of the pressure via the fracture width and the viscosity. If we drop out this F bar, it's Poiseuilleot equation for laminar flow. This F bar is an approximation, a Moody diagram that tries to approximate flow for all Reynolds numbers, including transition and fully turbulent ranges. And then tip boundary conditions. Now, what's interesting from a modeling perspective is that the flow back at the surface is either moderated by a turbine and or a turbine with a flow back moderating choke. So these experiments that are taking place in the field right now don't have a turbine there. They're just flowing back on a choke to understand lens behavior. It actually changes the algorithm, at least the way I had the algorithm set up, where I was originally, typical hydraulic fracture model, you impose the fluid flux at the well. Now the fluid flux is related to the choke diameter and the pressure. So it's a mixed boundary value problem, which sounds innocent enough, except that I actually ended up having to put in an entirely separate additional iteration loop around the entire code in order to satisfy this boundary condition. So here's how this thing looks, just as an example of the behavior. So here at we'll kind of walk through each piece. So this is the width. I'm using oil field units of PSI and inches and feet. So apologies to those who don't like oil field units. So it's starting at sort of 10 millimeters or roughly width at time equals 0, and then flow back commences. Fluid starts flowing out of the well, and the width decreases with time. As that happens, the wellhead pressure steadily declines in kind of a linear manner, along with the flowback rate steadily, slowly declining in a linear manner. The width at the wellbore is declining also steadily in a linear manner, but then it kind of falls off from a cliff. And that was observed in the field and kind of denoted by the engineers working on the time as pinching. We didn't really know the mechanism. We kind of hypothesized. This is why the model is called lobster, because it was originally meant to try to understand how pinching scales with with fracture size, fracture behavior, flow back rate. So here's how this thing looks in the fracture width evolving with time. And you can see that final stage of pinching. Right as this thing falls off the cliff, it kind of pinches into a donut. So that's where the width gets so small that the pressure gradient gets really high at the wellbore. It pulls that width smaller and smaller. You get this kind of self-feeding fire that leads to the falling off a cliff of the wellhead pressure and the rate. Okay, so what you want to do, like this is the kind of side note, what you want to do to design an efficient lens, you want to make sure that you have sufficient volume. You don't want to pull the thing entirely closed in your everyday cycling. You want to have more volume than what you need to cycle. The other part, which I won't show today, is, to get more volume, you need more pressure. If you're driving the pressure up so much that you're driving leak off into the fissures around the lens, then your efficiency also falls off. So you're kind of trying to operate this thing in a range where you have enough pressure to get sufficient width that's sustained through the entire cycle, but not so much pressure that you drive fluid loss to the formation. But the moral of the story I want to drive towards today is something more rock mechanics oriented than lens design oriented. And it came up out of a case study in the Western Canadian Sedimentary Basin, where they were studying the behavior of these lenses by creating a lens. They did this through 2 injections on 2 sequential days, totaling a bit over 300 cubic meters of fluid that was injected to create a lens. Then the lens was shut in for 2 months, and they came back and they ran a field test that involved 3 inflation cycles and then multiple flowbacks on different choke sizes. Now, there's a few things we know about what happened with those 3 inflation cycles and the associated flowbacks. One, we know something about the orientation, or we can ascertain something about orientation from tilt meter monitoring. So there's a surface installation of tilt meters. Those tilt meters all create a pattern of surface deformation that is consistent with a nearly horizontal lens. That was the goal, was to create a nearly horizontal lens. That was achieved through notching the wellbore, giving a very clean entry to the fracture, trying to associate with layers that might have high horizontal stresses due to having rock properties that are often associated with anomalously high horizontal stresses in a sedimentary sequence. So the tilt data indicates that was successful. The lens was nearly horizontal, maybe dipping at 15 degrees or something like that. There was additional interpretation of the tilt meters using a Kalman filter that was carried out by CSIRO. It's a Kalman filter that regularizes the inversion using a planar 3D hydraulic fracture model. So Anthony Pierce from University of British Columbia and CSIRO collaborated to develop this method, and it was applied by CSIRO to this field test, and they show that these nearly horizontal fractures are also nearly circular in shape. Not exactly circular, but nearly. We also can ascertain the volume of fluid that was lost to the formation for each of these 3 inflations. So the first inflation of the day lost about 28% of the fluid. That means the volume of the lens was about 78% of the volume of fluid injected. But the fluid loss decreases with subsequent inflations as the day went on. And it kind of makes sense because as the day goes on, the lens spends more and more time at higher pressures, and the pore pressure around the lens is elevated. And so the pore pressure difference between the inside of the lens and the surrounding rock pore spaces gets smaller, and hence the leak off rate is decreasing. So here's how the field test looks in terms of wellhead pressure, which is in red, shown reference to the wellhead pressure that would be associated with being right at closure. So right at the where bottom hole would be equal to minimum stress, which is the vertical stress in this case. So you can see the wellhead pressure starts out below, and then during the first inflation, here in green, wellhead pressure comes up. There's also a period of higher wellhead pressure during second inflation and third inflation. And then during the flowback cycles, which flow back at different rates due to different choke sizes, there's a drop in the wellhead pressure, even at some points showing this kind of pinching behavior. Here's another kind of pinch. Note there's these big bumps in the flowback rate. That's due to some nitrogen gas that was in the well. It would kind of blast through the flow meter and give erroneously high flowback rates until the nitrogen gas was cleared. So the true flowback rate should be considered down here where it evens out to after the nitrogen gas goes through the flow meter. So what's really interesting about this field test, as someone who was involved in the modeling, it's actually kind of scary as someone involved in the modeling, is they had some downhole measurements, not only of pressure, which is kind of, I mean, we often don't have downhole pressures. We have to ascertain it from the fluid density. But we have direct measurement of downhole pressure right at the fracture inlet, and we can subtract off the in situ stress and get a net pressure directly from that. But then what's novel about these field tests is that they developed a caliper system that went out through the slots that were cut in the casing. So the fracture was started from a slot cut from the casing and into the rock, and then calipers were placed out into that slot so that as the lens is inflated and then allowed to deflate, the width is able to be measured directly. If we set the width at 0 when the pressure is below closure, we can get this change in width. We can integrate the change in width to get a wellbore crack width. Now that is actually kind of scary from the perspective of modeling because we are usually not this well constrained by field data. And so you can usually play around with your model and you can match the pressure. You can kind of wave your hands at, well, my model says the width is blank and nobody can really argue with me. And so you kind of move on. But here we don't have the luxury of doing that. In fact, what we can do is take this pressure and width and take the quotient of them. So width divided by pressure, and we get a field determined value of the crack compliance in something like millimeters of aperture that we get per MPa of pressure. And so we can see that that increases during this initial injection, and then it kind of steadily increases, hovering around 3 millimeters per MPa. Now, during the times where the flowback is causing a drop in pressure, we get an overestimate of the compliance because of the fluid friction impacts. During periods of fluid injection, we get an underestimate, but they should cycle around the actual kind of elastic compliance of the lens. Okay, so here's where I think it sort of pops into sharp relief where our model is in a little bit of trouble. So let's look at the model now. So let's take a step back from the data. If I take a hydraulic fracture model for a circular lens, so any way you want to solve elasticity equations, if it is an elastic, open, circular fracture, then its volume is related and width are related to the radius, net pressure, and plane strain modulus via these classical LEFM relationships. From these, we can derive simply what is the elastic compliance. What's the width over net pressure? We have data for this. We also have data for in the field. We also have data for the volume of the lens because we know how much we injected and we know the fluid loss proportion because of the tilt meter data. We have well logs that give us an upper bound on the plane strain elastic modulus. We know the bottom hole net pressure. So we're really well constrained in the field to compare to the model. So the way I want to look at this is by taking my model results and my field results and normalize them by this right-hand side. So whatever I get from the model for compliance, I'm going to normalize it by the right-hand side. Whatever I get in the field, I'll normalize by right-hand side. If we look at model results, this is this normalized crack compliance, and plot it versus the lens volume, that allows us to track, this is lobster simulation, the change in compliance as fluid is injected, withdrawn, injected, withdrawn. And what we see is that the apparent compliance is underestimated during injection due to fluid friction. It's overestimated during withdrawal, but it cycles around 1. And actually, in this case, it's slightly above 1 because this fracture is close enough to the Earth's surface, and the Earth's surface is accounted for in the model. So if this was deeper, it would be exactly 1. Point is, lobster or any LEFM-based hydraulic fracture fluid lens model will cycle around 1 when normalized this way. You can't change it. You can play around all you want to with your inputs. You're going to cycle around 1. There's nothing else that you can do. Now, if we take the data from the field and we normalize it by the data we have from the field for the volume of the lens, the rock plane strain modulus, and the net pressure, we see that it is not cycling around 1. It actually cycles around a value of about 0.3. So the compliance is way, way, way lower than the LEFM compliance. And what this means is that if I start trying to calibrate or whatever I want to call my playing around with input parameters on my model to try to match it, I can't get there with any sort of realistic rock properties. The only way that I can match this is by artificially inflating the Young's modulus. And in fact, what I have to inflate it by is about a factor of 8. So I can match this if I just say, well, forget about the fact that well logs give me an upper bound of 15 GPa on the plane strain modulus. If I make it 120 GPa, I can match. But what on earth would this rock have a Young's modulus that's 8 times its value from well log? Why would this sedimentary rock have 120 GPa Young's modulus? And then the other piece of the mystery is as we cycle, the compliance goes up, meaning that if I want to match this by just ad hoc changing Young's modulus, I've got to keep making Young's modulus smaller with every subsequent cycle. Okay, so for the sake of time, I see I'm running very short on time. What we ended up doing was drawing inspiration from rock mechanics at multiple scales that evidence that when hydraulic fractures propagate, the crack front segments, this is from from the geosciences, segmentation, continued inflation. Here's the thing we focus on. It leaves behind these bridges. And these are like little springs that eventually break. So it ties the lens together with these springs that have a certain stiffness, a certain softening, a certain breakage. And field evidence that these exist in outcrops. We see these also across lab scale. So these are from Ruting Wu's PhD dissertation working with Leonid Germanovich. This is a segmented fracture that has petals, segments, and bridges. Plan view, it looks circular, but if you look at it from the side, there's these bridges that keep it connected, and we see them across all scales. So we model it by filling the lens with springs that have a certain stiffness and a certain softening law. So this is our spring law versus width. It looks a lot like a traction separation law. If any of you've done cohesive zone modeling, it looks a bit like that. You have a certain stiffness, a certain peak, a softening, and an ultimate displacement where it breaks. And when we substitute that into our model, we are now able to get the crack compliance modeled correctly. It lands in the right order of magnitude. It increases with subsequent cycles. We get the pressure and width, therefore, modeled at the same time. And again, for the sake of time, I'll just briefly show. If we look at the pressure and the width as measured for just a few sample example stages, the dashes are the simulation, the solid lines are the data, the blue is the flowing rate. We can match rate, pressure, and width all at the same time across multiple stages, as long as we account for the stiffness that's provided by these rock bridges. Okay, so to conclude, I think there's two behaviors that are pretty ubiquitous in rock mechanics, but that we often, maybe it's not always relevant, but sometimes it is. So rock failure is a time-dependent process. It can occur at load levels well below what's required for instantaneous failure. Acoustic emission signatures suggest underlying coalescence of microcracks that take place in a time-dependent way. And enhancements, for example, using a subcritical crack growth law can improve not only our simulation accuracy, but using these to guide us could improve things like uniformity of reservoir stimulation. I believe rock fracture also almost ubiquitously involves segmentation that results in intact bridges. And for those who've done experiments in the lab, how often do you break a rock sample, you take it out, and it still kind of holds together? And then you can maybe break it with your hands or maybe not. But that thing that makes it still kind of hold together, those are those intact bridges. And sometimes we might need to account for how those impact the compliance of the crack. Otherwise, our LEFM-based model really doesn't stand a chance of matching to data. It'll lead to under-prediction of pressure and length and over-prediction of width, if not accounted for. And that can be really important if you're doing hydraulic fracture simulation that is trying to design so that, for example, the hydraulic fracturing from one horizontal well does not intersect a nearby horizontal well. And I think it also points to the value of field scale experiments that measure both pressure and width. I think those are extremely valuable and would be great to have more effort put into that sort of level of data for field experimentation. And so thank you to QuidNet Energy, CSIRO, and helpful discussions from Arcady and Elena at University of Western Australia. If there's time left, I'm happy to take any questions.
Handy, Handy, this is
Oh,
Dee from Beijing.
oh, hey Dee, how are you?
Yeah, good. Great to see you just before sleeping. It's already it's nearly like 12 p.m. right now.
Yeah, great to see you.
Yeah. I did listen to your whole story, but I just there's this one point I'm really interested. You mentioned that fracture propagation may be delayed after injection, right?
Yeah,
During our operation, the field operation, we can see after pumping, after injection, not very long time, and we can see some from the macroseismic, there are some signals that far away from the wellbore, maybe like 12, 2 or 3 meters far away from the wellbore. But
yeah,
of course, at that time, the fracture do not propagate that far distance, that distance.
yeah.
I don't, could you please just explain?
Yeah, I mean, I think that so there's two things. I think actually that the seeing fractures farther away than they should be, I think could be further evidence of constriction from bridges. So I think that actually goes to the second point about bridges. As far as field evidence of delayed initiation, I would be looking at distributed acoustic sensing, and I have seen some data. There's not a lot published on this, but I have seen some data from like field tests that have been published in the literature, where if you look across multiple perforations in a stage, you see a perforation cluster that'll be quiet for a while on DAS, and then eventually you can see the fluid starts going through that perforation cluster. So that would be the sort of evidence that I would point to in the field of delayed initiation.
As a second point, you mentioned that fracture is much more much more than the perforation. You mean the second
Yeah,
point?
much longer than it should be. So constriction will lead a fracture to be much longer than it should be, much more quickly than it should get there.
Oh, okay. Okay, good to hear you.
So, um, Mungsu.
Thank you, Andy. This is very great. it's also very insightful to hear that controlling subcritical crack growth rate can achieve better control of development of fractures. I also trying to connect this part with the part that you say using different injection fluids, then you can achieve different breakdown pressure and time. So do you think these two can be connected, and how do we potentially do in the real systems to achieve better control of subcritical crack growth?
Yeah, so I mean, one thing that I didn't show, but we've published is in carbonates, you can get a decrease in delay time
Mhm,
by lowering the pH using hydrochloric acid.
mhm,
So that would be one aspect. So like really practically, hydrochloric acid included in the pad of a treatment could help with, this could be a mechanism by which that could help. Um, we also, um, so another aspect is if you look at this slope,
yeah,
this very gentle slope with the higher viscosity fluid, that's a good thing, right? That means that if there's variability in the stresses along the well, with this gentle slope means that variability along the well would give less delayed time. So it's possible also that having, larger viscosity fluid during the pad could also help to promote multiple fracture initiation and growth.
great. Thanks.
Thanks, Mungsu. Jeff.
Andy, that was great. Super interesting and kind of out of my wheelhouse. But the one thing that kind of struck me was when you mentioned these calipers that they have in the borehole that allows them to measure the aperture, and just having some experience of trying to do things in the bottom of a borehole that's whatever 1,000 feet away. Do you have any idea what this mechanism or what the thing is that they're actually putting into the hole that allows them to make this measurement?
Yeah, I do not. I my understanding is they were seeking or have been seeking some IP protection, and I have an arrangement with them that I don't want them to tell me,
Ah,
as probably all of us do, right? Don't tell me things
yeah.
I don't need to know because I don't want to be encumbered by what I don't need to know. But I'm sure that Quidnet, that team would be happy to share what they feel comfortable sharing. I just don't know exactly how they went about doing it. It
Okay.
was an experienced team that has been involved in downhole tool development for several decades that managed to pull it
Right.
off.
Yeah.
I don't know exactly how they did it.
Fair. That's fair. Yeah, I'm sure it's not. Yeah, I'm sure it's like surgery on some level.
Good. Anything else from you, Jeff? All right.
Great.
Same,
Pengju?
Pengju.
Yep. Hey, Pengju.
Andy, so I have a question for your energy storage part. So the
Yeah.
lens is horizontally, so it's perpendicular to the vertical. So is there any special reason for that? I think that is the reverse fault as can it be applied to other places that don't have that special geologic settings?
Yeah, so the crazy thing is they're able to do this in regions that if you just look on the stress map or at even at in some places where there are local mini frac tests or whatever, these are not in reverse faulting regimes regionally.
Okay.
So a couple reasons that it works. One is that they're not terribly deep. They're at like 1,000 feet, right? So the stresses get closer to each other. This contrast will get higher. The deeper you go, it'll be harder and harder to do this.
Yeah.
Second thing is there's a lot of layer by layer variability. Oftentimes those, for example, we know that if we've got very creep-prone layers. This is something Mark Zoback has talked about, is that those creep-prone layers will be high horizontal stress layers. Or if we have very high stiffness layers, that's more classically seen um, as high horizontal stress layers. So the idea is to kind of tuck up under those layers with high horizontal stress, get a very clean initiation, and then the fracture gets going in that horizontal orientation, and in that layered sequence where there's high stress barrier, it doesn't seem to tend to turn. That's all.
Okay.
That's the best I can do to explain it, but it's
Okay.
kind of remarkable. Yeah.
Yeah. Thank you.
Diego.
Okay, so anyone?
We have one. Yeah, we have Diego.
Hi, Andrew. Yes, thank you. First of all, just thanks for the presentation. I recently joined to ARMA, probably just like 1 month ago. This is the first meeting that I joined, so it's really, really great. It's probably just a simple question, but what is the basis of the testing on the rock? It was like a just intact rock or samples big enough to be considered like a rock mass?
Oh, so you're talking the lab testing?
Right.
Yeah. So the granite, sandstone, and limestone are all quarried samples. So, we're looking, those quarried samples are always very uniform, right? Like quarries don't tend to have a great business model in places with highly non-uniform rocks. And we were able to get repeatability with those as a result. So it kind of cleans things up so that you can understand the mechanisms. We did try on outcrop samples of Niobrara shale, and you can get delayed initiation in those, but not like every sample is so different from the previous one that it's very difficult to do a systematic study in those kind of more outcrop like and more heavily layered and heterogeneous samples. So the phenomenon is still there, but it's just hard to control it in the lab in such a way we can make sense of it.
I will think like probably there is an influence of previous existing fractures, right? That will probably modify the behavior.
I would agree. Yeah.
Okay.
Yeah.
All right. Thank you.
Thanks.
Dan, do you have a quick question if you have a second? Sorry, I couldn't figure out
Sure.
to raise
Hey,
my
Dan.
hand. Just also about the 3-point bending test. So you referred to that as brittle creep, and you held the load constant. Was there actual creep, like change in displacement under that constant load over time associated with? I would imagine as it increased the fracture.
Yeah, I mean, it
Just
actually
curious.
looks a lot like a creep, like a classical creep curve. If you took like a mechanics or materials of construction class and did creep in steel, it's not that dissimilar in that you get some kind of steady displacement increase and then a final burst at the end.
Okay. Great. Thanks.
Andy, I got one more.
Sure.
With your delayed fracture initiation work, have you tried like a hysteresis effect, like stress cycling them, loading it half the duration of what you assume to be the length of failure, backing it off, reloading and waiting? I just we worked on this 10 years ago with when I was with Gallium Adagurov. Really excited to see the progress that you've made, but what interests me is just from a cycling standpoint, with the time dependent nature, is if you get the same acoustic emissions. One thing Jeff and I, when we ran these tests, similar tests, hydraulic fracturing block tests, you'd have the rock complaint that you would see initially is what Roberto Suarez Rivera would compare the initial loading. And then if you reloaded, you didn't get the same acoustic emissions. The upfront responses. I was just kind of reflecting on if you could, through massaging at a lower initiation pressure and backing it off and bringing it back on, if you could fatigue the rock with time, with multiple cycles.
So we haven't tried it in rock. It's an interesting idea. I know that in the literature for glass, which obviously is amorphous and sort of a different story in some ways, but glass also does undergo both cyclic and static fatigue. It's obviously where like Charles did his original work and stuff like that. So you can definitely make a connection between static and dynamic fatigue in glass, basically just integrating the dynamic cycle, and they're fairly equivalent. Whether that play out in rock, we haven't tested. It's an interesting idea though.
Like the work's great. I'm really excited to see where you go with it from here.
Thank you.
Andy, I do have questions. So,
Sure.
first of all, this time-dependent initialization, would it be possible to reduce the required breakdown pressure to initialize a new factor, this behavior?
Yeah. So, and where that was kind of the original idea was in some formations where one needs to reduce that initiation pressure because you have a limitation. So most relevant for stress testing where where they inject from packers and you have a differential pressure limit on the packers, and sometimes they just can't get initiation, and it's a failure of
Yeah.
you can't get the number that the client wants you to get because you can't get an initiation. So that was the original idea, and it can work. The thing that is tricky about it is that there's this power law relationship, and so you don't really know whether you are an hour from initiation or whether you're a day from initiation. And so that's the practicality that can be tricky. Like if you're sitting out there with a crew, you can't, it's really, and that you can, the more you know about the rock, the more you can say, I think we're an hour away from initiation, stick with it. But if you don't have any acoustic emission detection, you know nothing about the rock, it's hard to say, hey, this is going to break down in an hour, wait for it. Or this is going to break down in a day, we should just move on.
Okay. So the problem is still the time period until the initialization is like needs more study. It's like an unknown now, right? Especially
To be able to characterize it, right? So that you can make a decision. Now, if you were detecting acoustic emission, that would help. So, if it was really a problem and you could deploy, like a fiber sensor in the Packers that could detect AE or a piezoelectric, like that would be the sort of thing, if it was worth it to you, you could simultaneously detect AE, and then you could really make a much more informed decision in the field.
Yeah, that's very interesting. I think that may be a future interest to more characterize for different rocks. Yeah, thank you.
Yep, no worries.
Okay. So seems like, is there any other people who have questions? Okay. If not, then thank you everyone for attending today's seminar. Very beautiful morning. Okay. And I would like to also announce our next speaker 2 weeks after the same time will be the Dr. Hafezer Tuis from the Itasca Consulting Company. So nice to meet you all, and thank you very much.
Thanks.
All right. Thank you, everybody.
Thank you.
Good to see you all.